Hang on, don't
do anything.
I'm just starting a whole new. Okay, we're live again,
Okay.
and we're gonna. Jeff, can you tell me if they're saying they can hear now? Are you on a new? I just started a new live stream. Or anybody else?
Oh, we'll be here when you figure it out, Nick. It's like such an awesome thing.
Audio good. Yay, audio good.
I'm on phone with CW operator. Oh, audio good. Yes.
Okay.
View stream is active.
Can you hear Nick? Thank you. Okay.
All right, great job.
Thank you. Okay, thank you for your patience. Everybody in here is obviously waiting as well. Can I double check with you one more time? And I can't see the live chat. Jeff? So you're going to tell me what they're saying in live chat. Can you hear me? Can you hear Joel? Joel 5x5, Nick 5x5.
Testing. This is Joel. Can you hear me?
Yes?
Sounds good.
Okay. All right. Thank you. Okay, everybody. Joel Gombiner, thank you very much. Here he is. Can you help me welcome Joel Gombiner?
All right. So let's get started. So it's really an honor to be here. So thank you, Nick, for the invitation and for organizing this whole series. This is wonderful to be presenting here. So today I'll be talking about the flood-carved channeled scabland of Washington, and in particular, I'll be focusing on one canyon of the system called Moses Coulee. And as Nick mentioned, I'm going to be presenting a different theory than typically considered. So many geologists think that Moses Coulee flooded from glacial Lake Missoula outburst floods, which is a huge lake that formed in western Montana during the last ice age. And today I'll be arguing that Lake Missoula was not the source of Moses Coulee floods. And instead I'll present evidence that floods into Moses Coulee more likely came from subglacial meltwater from the north. And it's not actually a new idea, but I've compiled new evidence and new reasoning for this old idea. The scenario that I'm going to be presenting is that large volumes of meltwater pooled beneath the Cordilleran ice sheet and then drained suddenly through networks of subglacial valleys to the ice edge, and that this produced large outburst floods that inundated Moses Coulee and other areas. So with that goal in mind, let's get started with some context. So during the last glaciation, which peaked around 18,000 years ago, most of North America was covered by the Laurentide and Cordilleran ice sheets. So the future sites of Seattle, Chicago, New York City were all beneath the ice when these glaciers were at their maximum extent. And it's fairly obvious from the geological record where the ice extended to, but it's far less obvious what happened beneath these ice sheets. And a major point of contention over decades has been to what extent lakes formed under and on the ice sheets, and whether these lakes produced large floods that flowed beneath the ice to the ice edge. By the beginning of the Holocene, around 10,000 years ago, most of the ice had disappeared, leaving behind the ice-free continent that we see today. And glaciers were more or less restricted to mountainous areas near the coast where there's lots of snowfall. And this deglaciation left behind vast amounts of geologic evidence about the nature of these ancient ice sheets. Got some bad news. The future is going to be ice-free if we continue on our present trajectory of carbon dioxide emissions. There might be a small ice cap left on Greenland, but more or less we've locked in a future where Greenland is going away. So some of the knowledge gaps in understanding this future have to do with the processes and timescales of big ice sheets, particularly how fast they can disappear and whether extreme ice sheet processes that we don't see today might accompany these periods of major ice sheet change. So with this in mind, what can we glean from the history of the Cordilleran ice sheet? So like the Greenland ice sheet is today, the Cordilleran ice sheet was once a continental ice sheet that was out of balance with a warming climate. And my work focuses on the southern part of the Cordilleran ice sheet, shown in this black box, because in my opinion, it's a fascinating and poorly understood system. So ice sheets, it's a bit of a misnomer. They're really domes of flowing ice, and they form from the buildup of snowfall that compresses itself into ice over time. And these large ice masses flow like silly putty under their own weight, creating rivers of grinding and flowing ice. Ice sheets often organize themselves into networks of glaciers that coalesce into major outlet glaciers. So looking at the southern margin of the Cordilleran ice sheet, 3 major outlet glaciers advanced into northern Washington and Idaho: the Puget Lobe, the Okanagan Lobe, and the Purcell Trench Lobe. Now, all of them had profound influences on the landscapes that they once covered, and they also affected areas beyond their direct footprint. So in addition to the direct effects that ice had on the land beneath them, these outlet glaciers disrupted the flows of major rivers with ice dams, creating huge and unstable glacial lakes. Lake Missoula, shown on this map, was the largest and the least stable lake along the southern margin of the Cordilleran ice sheet. It repeatedly drained through its ice dam right here, resulting in large outburst floods, known as the Missoula floods. These floods drained through the channeled scabland of Washington, and they left behind many traces of their passage, including flood-carved canyons and deposits of gravel, sand, and silt. So let's look at some examples of flood evidence on the landscape from Moses Coulee, shown in that black box. The main hallmark of the channeled scabland is huge canyons with no rivers in them. The absence of rivers in these canyons leads to the inference that large and anomalous floods in the past must be invoked to explain the existence of the canyons. Another hallmark of the scabland is bouldery gravels. These are evidence of deep and fast-moving water required to explain these deposits of huge boulders. Another aspect of the channeled scabland is flood-transported erratics. So the scabland is entirely floored by basalt, yet places like Moses Coulee are littered with non-basaltic rocks: granites, gneisses, quartzites. In this picture, you're looking at a boulder in Moses Coulee. It's an angular boulder. It's porphyritic granite. You can see these feldspar phenocrysts there. And this clearly doesn't match the local bedrock, which is basalt that you can see in the background. Rocks like this in Moses Coulee often occur in clusters, and many of them are angular, unlike the shaped and rounded gravel we saw in the previous slide. So it's evident that these angular erratics must have arrived in icebergs, which protected them from the erosive effects of the floodwaters. Some erratics in Moses Coulee have glacial scratches and chatter marks on their surface. This is a cobble of quartzite that has these scratch marks formed by glacial erosion, as well as these chatter marks. And these delicate features would have been eroded if the rock had been tumbling around in the floodwaters, but they're preserved because this rock was traveling in an iceberg. So to give you a picture of what this kind of thing looks like, a modern day example of a glacial outburst flood occurred in Iceland in 1996, when the volcano known as Grímsvötn erupted beneath the Vatnajökull ice cap. So this eruption ultimately resulted in the footage you see here. So in this event, a volcano erupted beneath a glacier, creating a large amount of meltwater. And the water did not drain out immediately, but it pooled in a subglacial lake, which eventually drained to the ice edge, resulting in that water draining out from the base of the glacier that you saw there. So in this footage, Also from the same flood located downstream from the volcano, you can see blocks of ice containing rock and sediment that are tumbling in the floodwater and floating downstream. So eventually these ice blocks come to rest on the landscape and they leave behind the debris that they carried. So we infer that a similar process to this created those erratic deposits that we were just looking at in Moses Coulee. So the generally accepted story of the channeled scabland is that Lake Missoula is the source of all the big floods. Floods were guided into different routes depending on the configuration of ice dams downstream. So as you'll see in this series of maps, the Missoula flood story involves the interplay between ice from the north and floods from Lake Missoula from the east. This map shows the areas inundated by floods early in the glaciation, before the Okanagan lobe had advanced across the Big Bend of the Columbia River. And in this configuration, Missoula floods would travel down the main stem of the Columbia and through the eastern Cheney-Palouse tract. Now watch what happens on the coming slides as the ice advances to the south. When the Okanagan lobe advances across the Columbia River, this blocks that flood path and it causes a lake, Glacial Lake Columbia, to form behind the ice dam. The configuration shown here with a partially advanced Okanagan lobe is the one that's believed to have sent Missoula floods into Moses Coulee. And we'll get back to whether that's a plausible scenario. At its maximum extent, the Okanagan lobe totally blocked the path into Moses Coulee and into Upper Grand Coulee. This significantly increased the size of Glacial Lake Columbia, and it restricted Missoula floods to the eastern channeled scabland. Then as the ice pulled back, Grand Coulee here reopened as a flood route, and the level of Lake Columbia dropped. And finally, once the Okanagan lobe retreated north of the Columbia River, the floods returned to their natural course in the Columbia Valley. And you'll notice Lake Missoula is now gone from the map because by this time the Purcell Trench lobe had also retreated north, draining Lake Missoula. So these later floods must have come from a different source. So this traditional story is based on much hard-won evidence and reasoning. It mostly works, but there's one glaring hole in it, which is Moses Coulee. So let's talk about the Moses Coulee problem, and this has been discussed for over 100 years. So as you saw earlier, Moses Coulee contains all of the hallmark evidence of huge outburst floods from glaciers, and there's no really scientific debate about whether glacial megafloods flowed through Moses Coulee. But it's long been hard to understand how exactly Missoula floods could have got into there. So J. Harlan Bretz highlighted this discrepancy in a paper that was published almost 100 years ago. And what he said is that scabland tracts are connected to each other except for Moses Coulee. And what he means by connected here is that there are channels and valleys that link floodways to each other. But the lack of channels leading into Moses Coulee was an enigma to him and others because all of the other floodways in the scabland have channels leading into them. So this view of no connection began to change a bit with the man pictured here, Larry Hansen. This is a picture from Gary Paul, who's in the audience, from a field trip in 1976, where Larry Hansen is discussing with UW students how floods got into Moses Coulee. And what Hansen did is he began to map some of the channels connecting into Moses Coulee. And based on his mapping, he made a more nuanced statement than Brett's, saying that there's no obvious surface connection. And I think he was probably referencing Bretz's statement above. So just to give you a sense of this problem or enigma, take a look at this map. This is an oblique aerial view of central and eastern Washington. Some of the things you can see on the map, you can clearly see the Columbia River flowing around the edge of the Columbia River basalts. And you can see cutting across the Columbia Plateau or basin or whatever you want to call it, dark brown areas where soil cover was stripped away by floodwaters and where the floodwaters actually ate down into the bedrock, creating these channel systems. And in between these darker colored areas, you see tan colored areas that stood above the floodwaters and retained their soil cover during the floods. So what I want you to notice here is the connectivity or the lack thereof between the flood scoured pathways and the Columbia or the Spokane River here in this case. So what you'll see as you look at this is that most of these channel systems connect directly to the Columbia River. So there are these spillover points leading into the eastern tracts that connect directly to the Spokane River, Grand Coulee connecting directly to the Columbia River, and then here's Moses Coulee, way out on its own, connecting to nothing, apparently. So the question is, where's that connection? What's going on upstream of Moses Coulee? So let's take a look at how Hansen saw this in his mapping. We're going to zoom in on that area. And this is Larry Hansen's map of channels leading into Moses Coulee. So he called these the Mansfield channels. These are the channels here on this map. And he favored the view that Missoula floods created these channels. So based on this map and other work, he created this set of scenarios shown here, where an advancing Okanagan lobe diverted Missoula floods from the Columbia River across the plateau and into Moses Coulee. One of the odd things I find about these scenarios is that he shows water traveling from the northeast to the southwest, yet the orientation of the channels is more from the north to the south. And I think that's a little weird. Richard Waite, another person who's worked on this problem for decades, he recently published a paper in which he developed Hansen's view a little further. He looked more closely at where water might have spilled into Moses Coulee, and he identified this point here labeled 654 with a red arrow as the place where water might have spilled out of the Columbia River through Foster Creek and into Moses Coulee. And another odd thing is that note that this doesn't go through where the Mansfield channels are at all. So we're going to get back to these scenarios in a little bit. But I want to talk about the way I've been thinking about this, which is continue on Hansen's work of mapping channels. So water-carved channels are unambiguous evidence showing where water actually flowed across the landscape. So I think Hansen was onto something with the Mansfield channels, but his mapping wasn't complete because he didn't have the same data and mapping tools that we have available today. So what you're looking at here is a map of the Waterville Plateau from 1933 made by Aaron Waters, and it shows what was a prevailing geologic view of the time. You can see the maximum extent of the Okanagan lobe with this line here, and you see Moses Coulee going through it and branching upstream into kind of this open Y shape. And then upstream of that, there's really nothing mapped. This is just a kind of blank void. And so this simple view of the glacial geology changed with Hansen's mapping. And he saw, okay, there's actually channels here on this plateau that lead into Moses Coulee. And now I want to show you my map that's expanded upon Hansen's map. And what you'll see is that the Mansfield channels are only a part of a larger network of channels. So what I see in this network of channels is a lot of connection. I see a radial system, and I think it's best explained by water flow beneath the Okanagan lobe. And I'm going to show you why I think this is difficult to reconcile with both Hansen and Waite's scenarios of water spilling over. But first, I want to give you a sense of how I made this map to convince you that it's not just a figment of my imagination. So let's take a closer look at a channelized area on the northeastern part of the Waterville Plateau. So again, this is an oblique terrain advanced view of a satellite image. This is rendered in Google Earth, and it shows an area that I think everybody could agree is dissected with channels. And to map these things, I used criteria. So the things that I mapped as channels are they're elongated depressions. So they're geometric features. They're low points on the landscape. They're anabranching, which means they split apart and come back together rather than dendritic. They often contain closed depressions. So if you look at this map, you'll see a lot of pools filled with water, and these are internally drained depressions within channels. They're typically in cross-section, they have a flat bottom rather than a V-shaped profile, and they're interwoven between streamlined residuals. And finally, you don't typically see active streams flowing through these systems. And I identified them both based on their appearance on satellite imagery, meaning that in this view, the channels are green because they retain water and stay vegetated, while the adjacent higher areas are brown, they're dry. And then I also looked at their elevation. Again, they're low points. So now I'm going to overlay my map of channels on this view, and that's where I drew lines on a map and traced out channels. That's all this is. And you'll notice it's not totally complete because there's a lot there, and I didn't have enough time. So the overall network of channels on the Waterville Plateau has a very different geometry from the eastern channeled scabland systems. So this is a topographic map, and now I'm going to show the channel systems. The eastern scabland systems have linear forms. They're elongated along pre-existing surface slopes where the surface water flowed downhill. And in contrast, the network on the Waterville Plateau has a radial form. The channels radiate outwards towards the former ice edge. And in my view, this reflects drainage pathways that followed hydropotential beneath ice rather than gravitational potential on the surface. So the channels leading into a Moses Coulee seem like they're less a part of a surface flood spillover network and more a part of a subglacial network. So with this in mind, I want to go back to Hansen and Waite's idea of a spillover. And to think about this, I want to talk about drainage divides and boundaries between basins. So I'm going to use an analogy here to help you understand what a drainage divide is. So drainage divides are boundaries between basins. Like think about this sink. Imagine if somebody left the tap on and the drain was clogged. What would happen? The water would overflow, but due to the walls, it would flow out the front. No water would go over the walls because they're much higher than the front-facing outlet. Pretty simple concept, right? So now imagine that the amount of water flowing into the sink increased substantially. The tap changes into a fire hose. Or imagine that the front becomes blocked with some kind of barrier. Now what happens? Water would start to pour over the walls, but it would first pour over the lowest point here on the front of the wall. And if the flow increased, water would progressively flow over higher and higher points on the wall, and eventually it would flow over the back wall. Okay, so that should be simple enough to understand. So let's extend this idea to the landscape. The idea that Hansen and Waite had is that a flood overflowing from the Foster Creek Basin somehow spilled over the drainage divide into Moses Coulee. So in both of their scenarios, the idea is that water from a Missoula flood coming in here fills up the Foster Creek Basin. And the reason it's able to do that is because there's ice here blocking that drainage pathway. And then it begins to spill over somewhere into the Moses Coulee Basin. So one point about this scenario is that it's nearly impossible if Grand Coulee exists in its present form. So going back to our sink, Grand Coulee is like the front of the sink. It's a huge outlet that can drain almost any amount of incoming water. So in our overspill scenarios, we have to imagine that this outlet is blocked. It'd be like putting a wall over the front of the sink. And then the divide between the Foster Creek and the Moses Coulee Basin, it's like the sidewalls on the sink. Oops. So with that same idea that water would first spill over the lowest point on the sidewall, water coming out of Foster Creek should first spill over the lowest point on the drainage divide into Moses Coulee. So on this map, that divide is shown by this line here, and it's color-coded by elevation. So white is lower elevations, pink and red are intermediate, and black is higher. So clearly, water coming out of this basin into this one should spill over at the white segments on the line, at the lowest point on the drainage divide. So what we're going to do is we're going to look at places on this divide and see whether we see physical evidence in the form of channels of water crossing the divide. So if we're going to start with the lowest points on the divide in this green box and this blue box and look at whether there's prominent channels that cross the divide there. So these are topographic maps. On these maps, white is high and black is low. So you can see some channels on the topography. And I would say there's some degree of channelization across the divide, but there's no sense of prominent channels going across these white lines, in my view. Instead, what we see is that the biggest channels are actually across the higher points on the divide. And this is in contrast to the expectation from the spillover scenario. Going back to the sink, this would be like water pouring over the back of the sink while no water came out the low point on the side or out the front. And that doesn't really make any sense. So let's take a look at this red box labeled Mansfield's, where the divide is almost 100 meters higher, 75 to 100 meters higher than it is on the boxes we just looked at. Now here, in this map, we see two prominent canyons crossing the divide. Each of them are about a kilometer wide. And for these to have formed, water must have overtopped this pre-channel surface here, which is above 750 meters. And in this scenario, the water would have been 100 meters deep at the lower divides where there's barely any channels whatsoever. In simulations of this and models, the water surface only rises to about 700 meters here. It's nowhere near high enough to overtop this surface and carve these channels. So it's not clear to me that there's any plausible set of conditions that could have had a spillover flood that formed these channels. So let's take a look at what this particular canyon looks like in the field. Here it is. You can see that some bedrock terraces on the side of the canyon. Here's the canyon cutting across from the Foster Coulee side to the Moses Coulee side. And you'll see that the bottom is filled in with sediment. What you also see in the foreground is some granitic boulders that are part of a recessional moraine that's basically just a decoration on top of this canyon. So let's look at some other divide crossings on the Waterville Plateau. Let's look at the channels in the orange box labeled Pearl Hill. So in this image, there's 3 prominent canyons. Each of them are about 1 kilometer wide, and they're tens of meters in depth. There's one, there's another, and there's another there. And there's even a couple more. So once again, for these channels to have formed, it would require a water level that would have had to overtop the pre-channel surfaces here of around 725 meters, implying a flood that would have been 50 to 75 meters deep at the lower weakly channelized divide crossing. So again, it doesn't make sense that if such a flood had occurred, it would have carved deeper, wider, and more prominent channels where it was just shallowly overtopping a divide and barely carved any across the low elevation divides. Finally, let's look at the highest channel system on the Waterville Plateau, located on the northeastern part in that black box here labeled Wilson Butte. And here, this black line is the divide, and there's 6 prominent divide crossings that cross pre-flood surfaces from 750 up to 780 meters. And these are particularly difficult to understand how a surface overspill could have created these channels. So there's some evidence that Glacial Lake Columbia briefly did reach a 750 meter level, but this level occurred while this area was underneath ice, when the Okanagan Lobe was blocking Upper Grand Coulee. So the main point here is that it's very difficult to explain why there's more prominent channels crossing higher divides. So I think a more plausible explanation for the carving of the channels on the Waterville Plateau is that they're subglacially carved channels. I want to introduce the idea of tunnel valleys, which are systems of interconnected overfit channels that are common across the Northern Hemisphere. This is an example of a tunnel valley network in Germany that formed beneath the Fennoscandian ice sheet. And here's an example of a tunnel valley system from the Saginaw lobe of the Laurentide ice sheet. And finally, this is the channel system on the Waterville Plateau. So we shouldn't be surprised that there's subglacial meltwater carved channels here. They're everywhere beneath the North American and Eurasian ice sheets. So how did water flow beneath the Okanagan lobe? How does water flow beneath ice? So water flow beneath ice reflects something called hydropotential. Water at the surface just flows downhill under the force of gravity. Under ice, water feels the overburden pressure from the ice. So where the ice is thicker, it's under more pressure, and where the ice is thinner, it's under less pressure. So water flows under ice to areas of thinner ice. It flows down gradients in hydropotential. So subglacial water on the Waterville Plateau beneath the Okanagan lobe would have flowed outwards towards the ice margin, and it would have followed the same radial pattern we see carved into the landscape in the form of channels. So this is the channel map, and now I want to show you a map of, or a model of hydropotential beneath just a simple model of the Okanagan lobe. And in this map, the orange colors are higher hydropotential, and the blues and purples are lower. So water flowing under this glacier would have flowed outwards towards the edge, and it would have flowed under the pathways that we see carved into the landscape in the form of channels. So it's kind of all makes sense. All right. So what I've just showed you is work I did for my PhD. And since then, I've been zooming out a little bit and starting to think about this problem on the continental scale, on the full ice sheet scale. So if you're with me and you accept that the channels on the Waterville Plateau are subglacially carved, that they're some kind of tunnel valley network, and you accept that Moses Coulee floods were subglacial in their origin, you start to wonder, where did this water come from? Where was the water stored, and how and why did it suddenly drain to the ice edge? So one of the ways I've been beginning to think about that is making the same kind of channel map on the scale of the entire ice sheet. So same method that I was using before, just drawing lines in Google Earth around the edges of valleys and channels. And I've started making a new map that I'm going to show you in this video. So we're going to zoom out from the scale of the Waterville Plateau to the scale of the whole Cordilleran ice sheet. And so there's our Waterville Plateau network receding into the distance. And it's at the edge of a massive system of tunnel valleys that could have funneled water, not only to Moses Coulee, but to the Puget Lowland, maybe to the eastern part of the channeled Scabland. So So, we can talk about how these valleys formed. They've probably formed over multiple generations of glaciation from multiple processes. But when I see a network like this, I find it hard to explain in any other way than water flowing beneath ice. Okay, so just take that in for a second. I mean, that's something we can talk about later. Oh. So I have one last point about Moses Coulee. Let's see. This is supposed to be animated, but this is a point about the rocks that we see in Moses Coulee and what they can tell us about where the floods came from. So here again is a map of the southern Cordillera ice sheet. And to this map, I've added some bedrock geology. This big orange zone is the footprint of the Belt Purcell supergroup, which is a huge area of Proterozoic, low-grade metasedimentary bedrock. And it floors the area beneath the Purcell Trench Lobe, beneath Lake Missoula, beneath many of the glaciers that fed into Lake Missoula. So what we often see in Missoula flood deposits is rocks from the Belt Purcell. One of the distinctive rock types that terrain includes is argillite. It's a low-grade metasedimentary rock. And this is a boulder of argillite on Rattlesnake Mountain, which is in this red box here. The interpretation is that this boulder traveled to the site in a Missoula flood, carried in an iceberg that came to rest on the side of the mountain. So argillite is a decent tracer for Missoula floods. Where you see it in central Washington, you can infer that it was brought there in a Missoula flood from western Montana. So I have spent a good amount of time in Moses Coulee looking at rocks and particularly looking for this argillite as some indication that Missoula floods came into Moses Coulee, and I've yet to see it. What I have seen in Moses Coulee are some unique, really cool rocks. Here is a rock in Moses Coulee. This is Augen gneiss. You can see these stretched out megacrysts of feldspar. And then this is another rock in Moses Coulee. This is a quartzite, and you'll see little red crystals in there, which are garnet. This is a garnet-bearing quartzite. So these are both rock types that occur to the north of the channeled scabland in some of the metamorphic core complexes that are roughly outlined in this red zone here. So we don't see the tracer for Lake Missoula and Moses Coulee, and we do see rocks that came from the north. So let's put it all together. The channel system feeding into Moses Coulee has this radial geometry, while the channel systems in the eastern scabland have a linear geometry. The biggest channels in that system cross the higher drainage divides, which is opposite to the prediction made by a flood spilling over. And the channel network on the Waterville Plateau is at the edge of a much larger ice sheet scale channel network. And then finally, there's no belt rocks in Moses Coulee, but there are these high-grade metamorphic rocks that match these core complexes to the north. So what I've presented is controversial. It's not widely accepted by the geologic community. And so I'd love to hear any of your most vicious critiques, comments, or questions. And you'll find a lot more about this in my dissertation, which is freely available online. It's called The Okanagan Lobe and Moses Coulee During the Last Glaciation. So thank you.
Thank you, Joel. We're going to do some Q&A, and if you could please repeat the questions for our home viewers because they're not able to hear the questions. So who's got a question for Joel?
Yeah.
Joel, love the talk.
Thank you.
I was wondering if you could talk a little bit more about those the preferential development of those bigger channels on, in fact, the higher drainage divide. is that, it seems to me that that would make intuitive sense if those are sub-ice channels, that your lower drainage divides basically have a thicker overburden of ice and maybe be harder for water to get through those channels compared to the higher ones. Is that shoot from the hip idea plausible? Is there maybe something more that you could look into that would further strengthen that idea?
Yeah, that makes sense. That actually, so the question was about the preferential carving of channels across higher divides, and the idea presented was that the ice would have been thinner there, and the ice would have been thicker over the lower topography, so there would have been lower hydro potential at the higher divides, and water would have actually preferentially flowed there. I think that could be relevant. I mean, I think another relevance is meltwater supply from the north. So the Mansfield channels here are directly south of the Okanagan Valley, which is probably one of the main conduits through which subglacial water was traveling from the north. So it could just be that they were, directly downstream from one of the main meltwater pathways. But I think what you're saying also makes perfect sense. Yeah.
Speaking of the meltwater pathways from the north, I zoomed out and showed some ways to get water there. The images or the videos you showed in Iceland, where that water was generated by a volcanic eruption.
Mm-hmm.
Do you need to have something generate large volumes of meltwater in a pulse like that, or is it a constant process that's happening in an ice sheet anyway?
Yeah, so the question was about how meltwater is generated in the ice sheet and whether you need an Icelandic style system with subglacial volcanoes to generate sufficient amounts of meltwater to result in floods. Is that basically the question?
If you need
Something special to generate meltwater. You don't. I mean, if you go to Antarctica, you have huge subglacial lakes that are unrelated to volcanoes. What you need is a place to store water, in part. One thing I'll say is that there are subglacial volcanoes upstream and under the former Cordilleran ice sheet on the Fraser Plateau. One of the critiques of subglacial floods has been that subglacial meltwater tends to drain efficiently out of the ice. So you have a volcano, it creates water, but that water doesn't stick around. It just flows out, and it's hard to actually store large amounts of water in an unstable configuration where you can build up a huge reservoir, keep it locked in for long enough, but then suddenly it releases. So that's why glacial Lake Missoula has been sort of such an attractive source, because it's easy to understand how you just fill up this basin, it destabilizes the ice dam, it all drains out, and then you just kind of repeat that filling and draining cycle. One idea that's been sort of presented for how you store meltwater beneath an ice sheet is that you have melted warm-based conditions in the interior of the ice, and then around the edge of the ice sheet, you have cold-based ice where the ice is frozen to the ground, and that provides a seal around the edge of the ice sheet. The ice frozen directly to the ground. So I don't know if that answers the question to some degree. Yeah. In the hat, the beanie, yeah.
I've got a question, Joe, and I apologize in advance, but if you're having such subglacial melt and cooling, could you assume that would give high pore pressure, have those glaciers start moving down slope? I don't mean surging like variegated glacier, but having that kind of motion, and then once the water drains, the surging will stop, and then repeat the process again with ice margins or more material.
Yeah, so the question is, if you have a large amount of subglacial meltwater, does that cause the glacier to flow faster and surge? And can you have cycles of having a lot of meltwater, having surging, and then kind of slowing down and then repeating? Is that kind of what you're thinking? Yeah, I think that's. I mean, there's a lot of evidence that the Okanagan, or there's thought that the Okanagan Lobe was a surge type glacier. In part, it clearly advanced much further south than anything else. We also see widespread drumlinization along the bed, these streamlined landforms. So I think that could definitely be a part of how the whole system is working, where there's surging going on, there's flooding, and then there's maybe a refilling process of some kind. Yeah.
If this slow melting sort of process in a non-violent Missoula flood sort of way could form Moses Coulee,
Mm-hmm.
do you have a theory as to why we don't see similar dramatic coulees in the upper Midwest?
Part of it is the.
Could you repeat the question?
Sorry. So the question is, why don't we see similar coulees in the Midwest, which was at the southern margin of the Laurentide ice sheet? So I have a couple thoughts on that. One is the substrate. Coulees form in basalt, and so having that basaltic material to erode into is part of the reason we see the landscape we have here. There is a lot of evidence for subglacial floods in the Midwest as well. It's less obvious. It's also somewhat controversial, but I showed the example of the Tunnel Valley system beneath the Saginaw Lobe that probably formed in a similar way. Another difference is the Cordilleran ice sheet versus the Laurentide ice sheet. So the Laurentide ice sheet formed over the Canadian Shield, relatively flat bed topography. The Cordilleran ice sheet formed over mountainous topography, which has lots of deep valleys in it, which are places where you can store that meltwater. Just a couple differences there. Yeah.
So when you're digitizing these channels in Google Earth, I'm curious, how easy is it to find those margins of the channels? Like, are you having to spend a lot of time picking up those traces, or is it just easy?
So the question is about drawing the channels in Google Earth and whether it's easy. And in some cases it's obvious, in other cases it's not. And one of the things I do is I look at imagery from different years. And in some years you see that green tan difference where the channels are really picked out by the vegetation. In other years you don't see that. Google Earth has a very accurate and high resolution terrain model built into it. It has a DEM of the Earth that's better than anything you can download. And the only way you can access it is by moving your mouse over a point and reading off what the elevation is at that point. You can't actually create a DEM with their elevation data. So some of what I do is just moving my mouse and drawing lines and looking at profiles and say, oh, is there actually a channel here? I mean, some of these things they're not deep channels. They're only a meter in relief. And it's subjective. So I would love for somebody to review my channel map as a KML and say, hey, I don't think that's a channel, or you missed that one there.
How does that potentially compare to like Washington LiDAR? Is there 1 meter LiDAR in that area that's not Google Earth?
The question was, how does Google Earth compare to LiDAR, which for those that don't know is light detection and ranging. It's a way of mapping the elevation of the Earth at very high precision using lasers, and it is not available yet for that area. It's collected. It's been collected by FEMA for Douglas County, and the USGS has it, and I've been told it's going to be released imminently, but I think the government moves slowly. Yeah.
How much of a channel do you think existed before the ice sheet showed up? Was the ice sheet came out and you already had somewhat of a channel with Moses Coulee, or with Moses Coulee formed just specifically from that meltwater coming off, you think?
Okay, so the question is, what was the topography like before the floods and before the ice age? And were there valleys and channels that were enlarged
Coulee, yeah.
in a particular Moses Coulee? Yeah, there's probably a reason it is where it is. Probably it was in a pre-existing valley that was enlarged by flooding. For one of the things you see along the sides of Moses Coulee are hanging valleys, which are former dendritic networks that used to drain into a much higher valley that's since been deepened and enlarged by the flooding. So those hanging valleys are evidence that there is an old water pathway there.
How high are those hanging up? Sorry, I know.
In some cases, a couple 100 meters. Yeah. So the lower Coulee is a great place to see those things. You see those in Grand Coulee as well. Yeah. Yeah. Lisa.
There's a glacial moraine that goes down inside of Moses Coulee.
Yeah.
And so how does that fit in with your idea of the chronology of how Moses Coulee formed and where the ice sheet had been when Coulee was formed?
So the question is about a glacial moraine that's in Moses Coulee. So in Upper Moses Coulee, and then how that relates to the sequence of events of channel carving and glaciation. And in the Upper Coulee, there's this canyon, and then on the floor of the canyon is a glacial moraine, which tells you that the canyon had to have been carved there before the glacier advanced into it. So, I mean, I struggle to think about that because I don't know how much of this topography was formed during the last glacial cycle and how much was formed during previous glacial cycles. I think it's likely that the Okanagan lobe formed prior to the last glaciation. There's no direct evidence of that. So, but that relationship you're talking about does require that the Coulee was carved before ice advanced into it. But I wouldn't read too much into that sequence. If I don't think the whole thing happened during the last glacial cycle. I think the topography could have been put in place 1 million years ago and then could have potentially just been reused during subsequent cycles. But yeah.
How about one more?
These are great questions. I do this all day. Yeah.
Has anybody tried to, you talked about like the whole network of channels that are maybe different ages.
Mm-hmm.
Has anyone tried to figure out the timing of those in terms of how old they are, or are there sequences of them? And I mean, can you even do that, and how would you do that?
I mean, I think, so the question is about the timing of channel formation and whether you can date the age of a channel. I think looking at the valley fill, looking at the sediments that are in the channel is probably the best, at least one way to do that. So you know that the channel had to form before all the stuff that accumulated in it formed or was deposited. There's no good way to directly date the bedrock. People have tried to do exposure dating on basalt to see when was it carved and when was this rock exposed, and that work is still kind of ongoing. So I would say the valley fill, yeah.
Presumably some of it was under ice when it happened,
Mm-hmm.
and it's hard to do exposure dating without solar.
Right.
And that's the real problem.
Yeah, that's true. But if it had survived through 1 million years, it would have more cosmogenic nuclides than if it was carved during the last cycle. Some people have done some thermochronology on valleys in western BC, and they inferred that they argued these were valleys that they thought were eroded by glacier action from the Cordilleran ice sheet. And what they saw was that the valleys were formed early in the Pleistocene, like 2 million years ago. And so most of the erosion happened during the first few glaciations, and then they were just kind of reused during subsequent glaciations without too much erosion actually happening. And people have looked at tunnel valleys elsewhere, like in Europe, have come to kind of a similar conclusion that these things get used over and over again without necessarily that much erosion happening in later glacial cycles. But that work is kind of ongoing. Okay.
Hey, let's
Is that
thank Joel one more time for a great talk.
Thank you.
So if you want to talk more with Joel one-on-one, please come on up. He's hanging around right now. Some of us are going over to have some Japanese food. You're welcome to join us if you want to just talk over lunch. There's also Cornerstone Pizza at 4:30. Joel will still be here. You can visit then. Plenty of opportunities to chat with our guest. Thanks for coming, everybody. Have a good weekend. We'll see you in 2 weeks. You hit your blue button is off. Good. So folks are going to come visit with you. I'm going to talk with these live folks just a little bit more. They're saying they love you. Good job. Good job. Excellent talk, Joel. Be swell. All right. You still with us, home crowd? Let me talk to you for just a sec. So a couple final words. First of all, can you hear me? This was a technical challenge today, and I want to give an introduction to our speaker now because you didn't hear the introduction at the beginning of this. So if you're watching this in replay, I want to make sure you know who you just listened to if you're still with us. 5x5, thank you. So we were lucky to have Joel drive over from Seattle this morning. He just finished his PhD at the University of Washington, a long process. We had Joel here right before the pandemic. February of 2020, he was here in this room giving a talk, and it was a very different talk than what he just gave. He was very early in his work with Moses Coulee, and he was not doing channel work on Google Earth. He was just trying to work with individual boulders. So he's made this incredible transformation pre and post-pandemic. On his committee, he defended his PhD earlier this fall. He studied primarily under John Stone at the University of Washington, and a name that I know that you know, Brian Atwater, was a key part of Joel's committee as well. And if you're kind of like, why do I know this guy? You maybe saw a video that I did with Joel back in May or June maybe, where we did some work just chatting, he and I just tagged along with him doing some field work up in the Mansfield Channel. So if you've not found that video yet and you're inspired by this talk that you just heard, there's a little bit of more detail with Joel and myself as we're walking around. So he's chatting with folks up at the front of the room right now, and I just want to say thank you. And if you are interested in more geology, less than 24 hours from now, I'll be back here tomorrow morning. Saturday morning, November 19th at 9 a.m. Pacific time. I'll be doing a Baja, BC session B. We did session A, and that exists as a replay if you haven't caught that. But Daryl Cowan, also from the University of Washington, will be joining us then. Bryce the Rock Licker is here. He'd like to say something. Would you like to be on camera? Bryce needs my keys. Thank you for your help as always. They closed it again on you? Okay, thanks. Whoops, can't get those folks on camera. I just want to say it so I can get it off my chest. I came in here yesterday to double check that I knew how to do this Talk Friday setup because it's been a couple weeks. And the OBS system crashed on me yesterday. And it crashed twice today. So the abrupt beginning to this video is because I had already started how did that go? I scheduled the live stream. I couldn't get it to start. So I never did do that one. We probably lost a few people waiting before 11:50. Then I started a new live stream and asked people in the new live stream to go back to the old live stream and tell them that the new live stream had started. We were up and running then, and in the middle of the introduction, apparently, the OBS crashed and the mic went out for both of us. So we started yet another live stream. So it truly was reminiscent of 2 years ago when I was live streaming from home on my iPhone using our home's wireless, and I would like suddenly, blorp out in the middle of sessions, and then people would have to find the new stream. So it's been a while since we've done that. It's not the university's Ethernet coverage. It's something going on with OBS, and I may or may not figure it out. But if you come tomorrow morning at 9 a.m. Pacific and enjoy session B of Baja BC, it will just be me and the chalkboards and hopefully a functional OBS. Okay. Still have almost 500 people. So thank you so much. I love you, and we'll see you next time. End stream. I'm going to go drink some beer with our guest. Backcountry Gary is here as well, and Jeff. Oh, I need to show you Jeff quick. Hang on. Do you want to be on camera real quick?
No.
Okay. All right.
Oh.
I'll keep you off. It's still going, yeah. So Backcountry Gary is here. You're looking at Joel talking to one of our students, and Jeff from Vinman's is conveniently hidden behind our undergrad. And Backcountry Gary and his son. Okay. You'd be okay if that's okay. Thank you. I'll do the play-by-play then. So coming in from the left of the frame is Backcountry Gary, who's visiting for the day with his son, Jesse, who's a brand new freshman in my Geology 101 class. So on the left in the hat is Backcountry Gary, and on the right, without a hat and a blue parka, is Jeff from Vinman's Bakery. Okay, all right. Okay. Thanks, everybody. Thank you for tuning in, and especially thank you for playing along with all those broken live streams. It'll be a mess when I go and find it in a second. Lisa, you're safe. I'm turning the camera off.